Hello and welcome back. Today I have a Risetime pulse generator, and it is from a brand or a company called Bodnar, probably in the test equipment community known for the GPSTO and also for the fast Risetime generators. I have here one of the latest, and I like to show you what it can do and what I use it for. Very quick introduction. If you're not familiar with the company, it's based in the UK. They have now a European warehouse, so this item's really shipped in 3 days from France to the Netherlands here. Yeah, you probably know them from the GPSTO. They have them in lots of shapes and sizes. I have the 2-port here that I will show you in another video. And they also have the antennas if you need better reception. They do a lot of other timing stuff here with the NTP servers. Also in the ham radio, they do a lot to stabilize your ICOM and your other transceivers. They have here dividers and multipliers. They are based in the UK, close to the Silverstone racetrack, and that's why they probably also do a lot of race simulators. So this is the pulse generator I've been using for a couple of years now. It is one of the first. It is not available anymore, but it does greatest job. 40 picoseconds. It is a fixed signal of 10 megahertz. Can be configured with the software. They still support that. And here they say indeed you can use it for lab testing, for bandwidth, Risetime testing, and that's exactly where I use it for, to verify the bandwidth of an oscilloscope after a repair or after a hack, to see if it really did what it's supposed to do. Some people can do TDRs, I don't use it for that. And here they said generating a wide spectrum with harmonics, so it's kind of a noise source, but it is harmonic, so the signal is not flat, it just goes like this. But we can see that on the spectrum analyzer, I can show that. But they have a new generation of fast pulsars, and the one I have here is this one, and it is variable frequency. For me, sometimes the 10 megahertz is just too fast and I want to test on a lower frequency. Also, this one is 30 picoseconds, so we can even just check a higher bandwidth. The frequency can be set from 30k up to 300 megahertz, which is really a lot, and well, it's kind of precise, 2 ppm. Usually it's not the frequency that matters, that it is so precise. It's more that you really want the Risetime to be a lot faster than your oscilloscope can handle, so you know exactly you're looking at the limit of your oscilloscope Risetime and not of the limit of the pulsar. I will be using the pulsar to verify the bandwidth of an oscilloscope. Of course, there are many ways to do this, but there are also many limits that limit the bandwidth of an oscilloscope. First, you have the analog circuitry, maybe we call that the analog bandwidth, that at some point when the frequency goes high enough, the analog circuitry or the op-amps just don't amplify that good, and then it will go down. But that you can easily check with the signal generator. You just put the frequency and then you go higher, 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 and at some point you see that the amplitude will just go down. Well, if you are about minus 3 dB or 70%, then you could say, okay, this is the limit of that. Then, of course, you also have the Risetime, and that is the test that I like to do. If the oscilloscope cannot rise enough from 0 to 1 volt, then your square waves start to look like a sine, because it just goes like this now, because it cannot rise fast enough. That is another limit. And of course the slew rate from 0 to 1 volt goes a lot faster than 0 to 100 volt. So you need to keep your voltage down doing this test, and that is why you also have your 1x 10x switch on your probe. They do not need to go these super high voltages, but to keep it low, because that will go a lot faster. Also, you need to realize that if you want to measure square waves on your oscilloscope, your bandwidth needs to be at least 3 to 5 times the frequency that you would like to measure. So that means when I use my old fast Risetime pulsar, it is fixed 10 megahertz. So my oscilloscope needs to be at least 30 megahertz. If that is not the case, it will start to look like a sine wave, because the Risetime is just not fast enough. So of course I have the product here, but also I have a lot of different oscilloscopes that I like to verify and then see how good this method is. So what I have here a Chinese one that says it should be 110 megahertz, which I doubt. We have here one of the popular Shaojis. I think this one is 10 megahertz. We can verify that, but not with my old pulsar. This one is 50 megahertz. That should be able to do with my old pulsar, but I will be using the new one, of course. I have a 50 megahertz, a 100 megahertz, and a 200 megahertz. The fast pulsar I have here is the LBE-1321. That is the new generation of the fast Risetime pulsars, and it's the one with the variable frequency. And I've got a nice card. And what does it look like? It is very small. That is nice. Comes with a seemingly good quality cable. Wow. It does look nice. It comes with an SMA BNC. That is the one I will be using. And there is even an adapter if you need to use it in another way. So let's have a look. That looks like an improvement. Here is the old one. It was a PCB all open, just to touch. You can see even the components. It has the old USB. It did have a trigger port, but that I think there is also one available from the new series that has a trigger port. I never used the trigger port, and it has a BNC. This one looks a lot nicer. They've put the brand on it, and here on the back you have the type numbers and everything. Here is the newer USB-C connection and the SMA, which I of course will use with the BNC. We are talking RF stuff, and it is 10 megahertz. So the voltage that comes out is around 1 volt, but only when it is connected to a load of 50 ohms. Well, the oscilloscope has a 1 megahertz input impedance, so I have here a pass-through 50 ohms. And we can connect it like this to the oscilloscope. Let's first try the minus 3 dB or the 70%. I put here my 50 ohms. I will do that directly in the signal generator here. I will do 1 megahertz. Here we go. Well, 1 megahertz shows up very nice, and now I'm just going to increase it. We should be able to go up to 40 megahertz, and after that the signal should go weaker. So we can just do it. We can see that it is going slightly down. We are now at 14 megahertz right here, and it keeps on going down, and now we are at 40 megahertz. And we can see that it really decreased a lot. So this is one of those limits. If I go now a lot higher, we will see it goes very fast down. When we look at the signal like this, we are at 40 megahertz. Let's say it was within the 70%. It is still very useless. So another limitation would be, but it's more practical limitation, is the time base. Can the time base be low enough? Because what if the time base could not go lower than this? It's kind of useless, no? The bandwidth then. But it's a Tektronix, so I trust it will be good. This is the lowest, and indeed this would be very useful. About the square wave, that the bandwidth needs to be at least 3 times. I like to show that also. So here we are at 1 megahertz. And we can see it is a very nice square, but it should be, because we can go up to 40 megahertz. But what if I go to 10 megahertz, and we going to zoom in? We see that it is already less of a square. And even though it is only 10 megahertz, with our 50 megahertz scope, you can see we already see a wrong shape, because it was a perfect square. So what if we go a lot higher? Well, now we are at 15 megahertz, and well, it is almost a sine wave already. So that means 3 times our 15, we are over this one. So you see that about 3 times, if I go now a lot higher, here now I'm at the limit of my square, but it is 25 megahertz. You can see it doesn't look like a square at all. So let's do that again. 25 square wave, put it on the Tektronix. It is well below the 40, but we need 3 times. And here we have one that can go up to 200, and look at the difference. And the slower the rise time is, the more it will become a sine wave. And that's why the rise timer is great to see the limit of the bandwidth. So the theory, you measure the rise time between the 10 and the 90%. I think this needs to be 1 volt. And of course we have a little overshoot that we don't look at. Because of the fast rise time, you will have overshoot. It's just a fact. And 1 nanoseconds will be around 350 megahertz. Well, and I put some table here so we can see the frequency. And the calculation is here with the rise time. Is your bandwidth in megahertz if these are nanoseconds. So we are going to use the pulsar. I put it in 50 ohms because we want to end up with about 1 volt. I put in the USB-C. We have the pulse on the screen. We can see it uses about 210 milliamps, not that much. Let's zoom in and see if we can see the rise time. Let's zoom in a bit. Usually the more you zoom in, the better the readout becomes. Let's see in the measure menu if we have rise time or not. Yes, we have. It thinks it is around 6. It jumps from 5 and a bit to 6. So let's say 6. If I do like this, yeah, it jumps around 6. So how much would 6 be? Now 6 and 6 and a bit, that would be between the 50 and the 58. So that is very close, and even a little bit more than the 40 megahertz. I have here a lot older oscilloscope, also Tektronix. It should be able to get up to 100 megahertz. So I use the same pulsar, and let's see. I am not sure this one has the proper measure menu that we can see the rise time. I think we need to try to see that ourselves. The measure menu doesn't give us rise time, but we should be able to determine it. If I try to get it here in one line, we are in 5 nanoseconds, and we can cut a little bit off here, and then we are within. So let's say it is around 3, then 2.5, 3. Well, the readout is of course not that precise, but if we are in 3 or 3.5, we are here within the 88 and the 110. So we could say, yeah, okay, 100 makes sense here. And the more modern is a lot more easy because they have the measure menu. I can maybe zoom in a little bit more. Then we go to the measure menu, and we can see here the rise time. It's a bit full. But here we have the rise time. It is jumping between 1.3 and 1.5. Maybe it becomes more stable. Yeah, now it's more stable. It says, yeah, still 1.3, 1.5. Yes, well, if we see 1.5, we are around the 230 megahertz, and that's about correct because the oscilloscope is spec'd for 200. Okay, now I want to use it for 10 megahertz oscilloscope, and then the signal of 10 megahertz will be way too high. So let's see if we can switch it down to 1 megahertz. It comes with its own configuration software. I'm not sure if it will create a COM port, and we need to deal with all that because of course I have already lots and lots of USB devices. So I just start the program. I will now plug in the device, and it automatically detects it already. It says here it is a COM10 in the bottom, but that device is switched off right now. Yeah, it will pick automatically a port, and I don't need to do anything about this. That is great. This is the frequency, so let's just make that 1 megahertz. 1, 2, 3, 1, 2, 3, 1 megahertz. Okay, I just push this thing, I think. Okay, it should be 1 megahertz. That was easy. Here you can also change your amplitude if this 1 volt into 50 ohms is not correct, you can fine tune that here with new values, but I just keep it as it is because they probably calibrated it. So we have the 10 megahertz oscilloscope here, at least that's on the spec sheet. And well, we see already one thing, it does show, and maybe it's within the 70%, but this is another practical problem that the time base cannot zoom in. So maybe it did the 70%, we didn't test, but it is useless because of the time base. The rise time is now also makes no sense because we cannot zoom in that fast. But let's go to 1 megahertz. That would be easier to see. So at least we can then determine. Okay, I try to zoom in a bit. I'm now at the limit of my time base. The time base is 100 nanoseconds. And if we take here 10% off here and 10% off here, we are probably around 30 and 40 nanoseconds, which will be around, so that would be around 30 and 40. So we are indeed between the 9 and the 12 megahertz. But we already saw on the practical side that it is actually not the case because we couldn't really zoom in because the time base was the limit here. So this was a nice example why it is an added value that you can change it from 1 megahertz to 10 megahertz or the other way around, and you can even do it from a few K all the way up to 300 megahertz, and that if you use TDR, so the time domain reflection. So if you want to measure the length of the cable based on the reflection of the signal, then it becomes, depending on the length of the cable, you want to be able to change the frequency. Another use case could be probe compensation. Usually you do the probe compensation here on the low frequency like 1K, and you try to adjust this as good as possible. If you have better probes that are for higher frequencies, you have even more adjustments. Here I have two others, and this is a test tech probe, and they tell you here that you can measure this with 1 megahertz. You do the low frequency compensation here on the 1K, but the high frequency compensation you do here with 1 megahertz. And yeah, it's great if that 1 megahertz that you use, of course, has a very steep, fast rise time. And then they say you can use it broad spectrum as sort of a noise source. Well, that's my interpretation at least. We can see here this is the old pulsar set to 10 megahertz. And you can see this is between 0 and 3 gigahertz. We have a lot of stuff going on here, but we should be able to test the filter. The new pulsar shows this. So you see there is a lot of noise in the bottom, and then later it becomes. Now I'm doing a scan from 0 to 100 megahertz, and you can see here all the harmonics going on, and maybe we can see that better. Here we can see there is quite a lot, but we can actually use this. So what if I want to test a band filter? I have here a 10 megahertz band filter, so then we shoot something like this, I think. And with the filter, we can see indeed that it is only passing around the 10 megahertz. Maybe if we do the stop frequency a little bit lower, like 30 megahertz, we can see a lot better. You can still see the harmonics, but you can also see that the filtering does work with the band pass. So that is what I use the pulsar for, measuring the bandwidth of an oscilloscope. Still, you need to do all three tests. The amplitude 70%, the rise time, but also the usability with the time base. We saw this one, 10 megahertz, was okay, but usability with the time base was just below. Here I have a 50 megahertz also from Shoji, and it was around 35 megahertz with the rise time, but with usability it was quite close to that too, but 35 is not 50. And we had the same with this. This is an old Verneersi. It says 110. Well, with the rise time, I came about 60 megahertz, but with usability, not even around 30. So These specs are nice. One spec with the analog bandwidth maybe works with the amplitude, but then with the rise time it doesn't. And of course with usability, the time base is very important for me too. You need to see a whole wave and not like 10, because you cannot see anything. And all these three, the lowest of course is the effective bandwidth usability. Also very well done on the software. It does create a virtual port when you try to adjust the settings, but you don't need to worry about it. It just detects the device automatically. You are able to adjust a little bit the amplitude, which is great because maybe your 50 ohm pass-through dummy is just a little bit different than the one they used. And also the frequency, of course, you can do from a few K all the way up to a 300 megahertz, which is great. Thank you to Leo Bodnar for sending me the new pulsar. I'm already a happy user for many years for the 10 MHz pulsar, but this going to 1 MHz or even higher if I want to go higher is a great added value to this device. Thank you for watching, and I hope to see you next time.